Hello everyone, so welcome to the video lectures about the AI game playing. So AI game playing will refer to the ability of the computer that play games. We will think that playing games usually it will require the human intelligence because we need to have some strategies, we need to have the problem solving skills and also some decision making skills. So that's why so this is a subfield of this AI research. We would like to have an AI that can play game well. And so today we are going to take a look at this AI game playing. And this is the outline of today. So let us start with a simple game. I think all of us know what tic-tac-toe is, just in case you don't know what it is. So this is the tic-tac-toe. First of all, we have a 3x3 grid. And then you and also the AI will try to paste the symbol, cross, or the circle on this grid. Okay, take turn to do it. And then the goal is to form a straight line of three symbols, whether it can be horizontally, or vertically, or diagonally. And you place it here. So we will have our strategy to win, and then at the same time, if we have an AI that can play tic-tac-toe, it will also try to use this strategy to win this game. And here we have a concept. We say the game state, what it is. When the AI try to play this game against you, and you will try to keep track of what's going on with the game. For example, the positions of all those symbols so far up to this moment, and then whose turn it is. Okay, based on this information, then the AI will try to make decisions. Then we call it the game state, okay, including all the informations. The state will change when the game proceeds, which is whenever we finish our move, okay, put one of the symbol, then the state will change. For the AI, okay, here we say that for the game, okay, we say the game start from initial game state. Then for tic-tac-toe, the initial game state is empty board, which is the one here. Okay, we don't have anything, okay, any symbols on the board yet. And then we have the goal state as shown on the screen. We form the line. This is a vertical line and this horizontal line. And from the initial state to this goal state, there are many possibilities. Okay? There, we call it the state space. The AI will try to move, okay, from one state to another by placing those symbols. So hope that eventually it can reach this goal state. But then how it can be done? Okay, there are different paths, okay, that lead to this goal state. How can AI ensure that, okay, we are going to the right directions? And that's done by search tree. We say game playing is a search problem. Why do we say so? Given the state, let's say here we are now playing tic-tac-toe with the AI, and the AI now facing this situations. So this game state, we have already 6 symbols on the grid, and then now it's the turn for AI to put the O, or symbol O, onto this. So what should be the next move? So now AI will think about, okay, given this current game state, then there are 3 possibilities. I can paste the O here, here, or here. And we try to expand from this current state to this 3. Okay, that's one step ahead. And then, well, after the AI make the move, what will happen? Then come back to our turn. After we paste the O, then the player will have two possibilities, right? Then that's the two level, okay, two step ahead. The whole thing we call it is the search tree. The AI will try to think, okay, which possible move will eventually lead us to the goal state, and then it try. Okay, it is quite smart. Okay, not just think of one step ahead, because at this stage, okay, at this level, AI don't know, okay, which one is the best. Have to go one step further, and when we have the second step, okay, then we know which one is better. For example, for this one, after we paste the O at this position, and then the player pastes the O, the cross at this position, then we only have one position left, right? So the next O will be here, and which means the AI win. Okay, that's very nice. And how about this? In case the player pastes the cross at this positions, and the AI have to paste the O at this position, again, AI will win. Then how about the other two possible moves? For this one, just, well, it may win, and this one, well, just a draw. Then how about this move? Okay, for this move, then the AI will win. But then for this one, well, again, a draw. Then which one is the best? Okay, so you know that the AI will choose this one, because it will has a higher chance to win, right? So the AI will choose this one. Then we say the whole thing is a search tree. Then we just go through the tree, okay, keep exploring until we find one that can finally lead us to the goal state. Well, in this case, we only have three possibilities. Then will sound like it is quite easy, right? But then what if we start from the initial state? Then initially we will have a line possibility, right? So when we expand this initial game state, then we have line nodes. And for each of this node, we have 8 possibilities. And then for each of this 8 possibility, we will have 7 possibilities. So on and so forth. Then you can imagine, wow, the search tree is now very big. Right? The number of possibility grow very fast, okay, with each turn. Then it will be difficult for the AI to evaluate, okay, which one is the best. It will take a pretty long time to do it. It's actually in the past the computer is not that good, and it may not have enough memory to evaluate all the possibilities. Then we will think, okay, whether is it we really need to go through all this possibility. How we play the tic-tac-toe? So I'm not a clever, so I cannot go through all the steps. So if I am at the one who start the game, okay, I have the starting positions. I'm at the initial game state. I will place the O in the center. Okay, why? Just by my memory, I remember that if I will have a higher chance of win, so that's why I paste it there. Okay, so basically there exists some method that we do not need to go through all the stuff. Okay, we can hopefully we can find some evaluation formula, so that even though we don't go through the tree, okay, from the initial state to all the goal stage, we can still figure out, okay, which move is the best. Provided that for AI, okay, they always deal with number. How can we find out such a number, such a set of numbers that can help us to make the decisions? In tic-tac-toe, okay, how you do it is like there's something called the heuristic evaluation functions, in which given a game state, it can do some calculations and tell you the possibility of winning. Like if we are facing this game state, then it will tell you the possibility of winning is 1. And then for this one, the possibility of winning is 0.5. And then for this move, the possibility of winning is also 0.5. Then you just do comparison among all those numbers. You take it out, okay, this is the highest probability. Then we go forward to this. Okay, you reduce the numbers of moves that we have to consider. Okay, reduce the search space. We just choose the one that gives us the highest possibility of win. Then we call it this, the heuristic evaluation function, and this one is for the tic-tac-toe, and that's for tic-tac-toe. For the tic-tac-toe, how we build the heuristic evaluation function is like it will consider some factors. Let's say whether we whether we can control the center of the board, okay, whether we can board the opponent's winning line. Like this kind of factors will build this heuristic evaluation functions, because for tic-tac-toe is rather simple. Okay, but then for the other chess game, then you will know that it will be very challenging for us to design such a heuristic evaluation functions, because there are many factors, and then the tree will be pretty big, which means we have to also consider the long-term effect of all those moves. And that's why at that time, people want to tackle this kind of chess game, because they think that if I can build such an AI that can tackle this kind of chess game, that means the AI is very intelligent. So at that time, this chess is a very popular subfield of AI. They spend a long time want to develop such AI. For this chess, we have 8x8 grid, and we have to also consider the presence and absence of all those pieces, which means there are many possibilities to consider. Just until one day we have the Deep Blue, and we have Deep Blue that finally we can tackle this chess game in the 1950s. This is a video that shows you the history of this Deep Blue versus the world champion, the Gary Kasparov, in 1997. So I am not going to show this video here. If you're interested, go to the slide and then click the link, okay, and watch the video. And at that time, 1997, finally we have the AI that can beat the world champion, and that is a very significant milestone in the AI research, which means we can really build such an AI that can win the human level performance in the chess in this kind of complex domain. And so people start to working on more advanced AI system. For this Deep Blue, so why do we call it Deep Blue? First of all, it is developed by IBM. It is a supercomputer that can play chess in 1997, as shown here, with the world champion. So for this Deep Blue, so why we say it is deep? Because this Deep Blue can have, you can search for depth of 6 to 8 moves, which is 6 to 8 steps ahead. And for some situation, you can even have the depth of 20 or more than 20 moves. Although it will take a longer time to for the deep blue to make the decisions. And so that's why we call it deep, because it can think more steps ahead. Now, how does deep blue evaluate a state? Okay? How people build this heuristic evaluation function? It is a very complicated, complex functions, and there is 8,000 rules that people. This is decided based on first 4,000 open books. The open books tell. We study the open books, and then the open book can tell and help the researcher to build some rules, design some rules for the open phase, and then there's 700,000 game master, grandmaster games is used to set the rule that is to evaluate positions and also to make the decisions, and also they refer to some end game database. Okay, and this time this one is for the end game. There's several steps. Okay, how to end the game so that finally the AI can convert the advantage into winning. Since this function contains 8,000 rules, and so it is pretty computationally intensive. So that's why it required a very powerful machine to do the computation in which that is a deep blue. A deep blue is a supercomputer that is designed in this way, designed to handle this computational demand of this heuristic evaluation functions. Then finally, we have deep blue that can tackle this chess, and people start to go further to even more complicated game, which is this Go. Okay, Go. 19 times 19, which is pretty big. And then if you look at the state space, and it is 10 to the power 172, which is very, 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 very big, and which that is even supercomputer cannot handle it. Then how can we do it? Okay, finally, we have AlphaGo that tackle this this game. In this 2016, then we have AlphaGo versus at that moment the world champion, okay, Lisendo, in the match 2016. Okay, that the AlphaGo is developed by the Google DeepMind. That's a computer program that played this board game Go. And how it works, we just go briefly, say why it can handle such a large search tree. So we say that well, the search tree is so big, it is not possible for us to go through all the possibility. But how about we just go through part of it? The first trick of AlphaGo is this Monte Carlo tree search. If you are interested, you can look at this article about this Monte Carlo tree search. But basically, it is that we're not going through the whole tree. Okay, we're just trying to go through part of this tree which are more compromising. How does it work? Okay, starting from given positions, situations, we try to build a tree. Okay, try to do the simulations of all those possible moves, and then to find out the move that can give us the highest possibility to win. Okay, first of all, we start from positions. Let's say we have 4 positions, 4 possible moves, and then for each of these moves, we do the simulations. Okay, to see that, okay, if I go that way, how many times I can win. Okay, you can see that, okay, here we have 4, and after some simulations, we find that, okay, this should be the most compromising branch to go, and then we pick this one. Okay, go further to explore it, and finally, okay, we should be able to find one that is with the highest probability of winning. Then that is the Monte Carlo tree search. We are not going through the whole tree, but then we're focusing on those branch that with a highest possibility of win. Then that's the trick one. And AlphaGo combine this Monte Carlo tree with deep learning. Okay, deep learning is neural network. Okay, deep neural network. Here there are two deep neural network. First of all, the policy network. Policy network can help us to predict the probability of each move given a position of the ball. It's like giving you the probability distributions. Okay? As the Monte Carlo tree, we'll try to select some branch to explore, right? Then this policy network can help the Monte Carlo tree to give smarter selection. So instead of trying all the possibility, you try to pick some move that the expert will choose. And then for the value network, okay, now we pick some branch to explore, but we don't know which one is the best. And so this value network can predict the possibility of winning. By giving all those positions on board, then it can tell you how good or how bad a position is. So among all the suggested branch by the policy network, then we can evaluate which branch is the best. So that's how the AlphaGo combine the deep learning with the Monte Carlo trick. And they have also one more trick. Initially, this AlphaGo is trained by those human expert games. They try to study the human expert game and train the neural network. And after this initial state, well, they even let the AlphaGo play by itself, which is the AlphaGo versus AlphaGo. And so they can now think out of the box. And they can now try some way that even the expert will not do that. Okay? Try some of the moves that the expert can never think of. So eventually, the more simulation that they have, they become more and more powerful, and eventually it have a better way to play the game than human and win the human champions. So that is well, briefly how AlphaGo work. So here we can compare this Deep Blue and AlphaGo, and we say that the Deep Blue is using the symbolic AI, in which we base on the expert knowledge, based on the opening book, based on the grandmaster book, the end game book, to try to handcraft, to design some rules for the AI. We just Deep Blue. They have 8,000 rules to do it. And then, well, it's okay for chess, but then we'll find out that for those problem with many possibility like Go, symbolic AI doesn't work. Deep Blue, that approach doesn't work. So that's why we have this AlphaGo, which uses connectionist AI. We have the deep learning, and then learn from the data in the initial state. And then we have the AlphaGo pay by itself, a trial and error. And then at the end, we have very powerful AI that can beat the world champion of Go. So that is the history. For the AI gaming, there are more applications. So not just Go, not just chess. It can also be used even for this webcam, the machine. Okay, this vacuum cleansing robots. Okay, let's say we have this two 4 pens. So how can we use an AI gaming concept to handle it? Then here we can consider the state, okay, like this. So the game state for the vacuum cleansing machine. Then we can consider the location, okay, location of the robot, the orientation of it, and then also the location of the dirt, location of the obstacle, and the area to model this game state. And then then for the AI is trying to do the search so that we know how to, or starting from this initial state, we can finally reach the goal stage, which we can finish cleansing all the things, and then maybe we can return to certain positions, and we try to find out all the intermediate steps. Okay, so vacuum cleansing machine, we can also use the AI gaming to make it work. Same for then for sure we will use it in all those video games. Okay, Pac-Man, okay, like this one. We have the NPC, right? So NPC will be the we can use AI. And also for those robots and also drones, we can use the AI gaming concept. Yeah, to summarize, we learned how AI gaming works. So basically, it is a search problem that we know game state, what it is, and then so there exists a game tree. We would like to start from the current game state, try to figure out how we can move so that eventually we can reach the goal state. We also take a look at 2 examples, the Deep Blue and also the AlphaGo. Instead of go through all the possibility, they will use the heuristic evaluation method using the deep learning methods so that the AI know how to see that move, and for sure in a quicker, faster one. So here is the reference. So that is for this lectures. Bye bye.